Bismillahirrahmanirrahim. I am Dr.Asad ullah, lecturer, Institute of Numerical Sciences, Cohort, University of Science and Technology. Dear students, welcome to the course of Fluid Mechanics, course code MATH-361, lecture number 9. We are in chapter number 2, Fluid Kinematics. In the previous lecture, we discussed some problems on Eulerian and Lagrangian description, and also discuss some basic definitions, that is the control volume, control surface, and infinitesimal fluid element. Then we discussed the behavior of fluid element in the flow field without going to the proof of the mathematical forms of these flow behaviors. In this lecture, we will try to discuss the following points. Number 1, material derivative. Number 2, problems on material derivative. We will discuss material derivative and its derivation in detail, and then we will discuss some problems on how we use the material derivative by solving some numerical problems. Number 3, we will discuss some basic definitions, that is the volumetric flow rate, mass flow rate, and mean velocity. Number 4, we will derive the equation for the volumetric flux through a surface. Number 5, there will be some problems on the volumetric flux through a surface. Number 6, some practice problems will be given to the students. And finally, there will be references. Now, what is material derivative? Consider an infinitesimal fluid element which is initially at the point 1 and has the velocity v1 at this point. After some time, it moves and occupies the point 2 in the xyz plane. Here the infinitesimal fluid velocity is v2. Here I, j and k are the unit vectors along the x, y and z axes respectively. Now the velocity vector in the Cartesian plane is given by v is equal to ui plus vj plus wk. Here the velocity components u, v and w depends on x, y, z and time t. Similarly, the scalar density field is also depends on x, y, z and time t. Throughout this lecture, the boldface notation will be used for the vectors. At the initial point 1 and the final point 2, the scalar density field is given by ρ1 is equal to ρ1 is the function of x1, y1, z1 and t1, and ρ2 is equal to ρ2 is the function of x2, y2, z2 and t2 respectively. Now, expanding the density ρ about the initial point 1 in Taylor series, we get ρ2 is equal to ρ1 plus partial derivative of the density with respect to x at the point 1 times x2 minus x1 plus partial derivative of the density at the point 1 with respect to y times y2 minus y1, and similarly with respect to z and with respect to t, because ρ is the function of x, y, z and t, and plus the remaining higher order terms. Now adding minus ρ1 in both sides of the previous equation and then dividing by t2 minus t1. It should be noted here that if t1 and t2 are equal to each other, then we cannot divide by t2 minus t1. So dividing by t2 minus t1 such that t1 and t2 are not equal, and ignoring higher order terms, we get the result in the form of equation 2.1. Now in the limiting case, we can write ρ2 minus ρ1 divided by t2 minus t1 as t2 tends to t1, and this expression is equal to d rho over dt. Here the symbol capital d rho over dt is the instantaneous rate of change of the density as the fluid element passes through the point 1. We know from the basic calculus, when time t2 tends to t1, the ratio x2 minus x1 divided by t2 minus t1 is equal to the velocity component u. And similarly, y2 minus y1 divided by t2 minus t1 is equal to the velocity component u. And similarly, z2 minus z1 divided by t2 minus t1 in the limiting case is equal to the velocity component w. So, taking the limit as t2 tends to t1 of equation 2.1, we obtain equation 2.2. Here, d rho over dt is equal to u times partial rho over partial x plus v times partial rho over partial y plus w times partial rho over partial z and plus partial rho over partial t. Examine equation 2.2 closely. From it we can obtain an expression for the substantial derivative in Cartesian coordinates as given in equation 2.3. Here, the word substantial derivative is used for the material derivative because material derivative is also called substantial derivative, total derivative, or Stokes derivative. Now, further in Cartesian coordinates, the vector operator nebula that can also be written in the form of equation 2.4. Hence, equation 2.3 can be written in the form of equation 2.5. Equation 2.5 is the vector form of the material derivative. In this form, the first term partial rho over partial t is the local change with respect to the time t, where v dot nebula is the convective change. So, material derivative is the total derivative, that is the sum of the local change plus the convective change. Problem number 1. Given the velocity field v is equal to 3ti plus xzj plus ty square k. Here I, j and k are the unit vectors. Find the expression for the acceleration of the fluid particle. Now in solution, the acceleration for the fluid particle is given by equation 2.6. This is the expand form of the material derivative. Now we know that the velocity field is given by this equation, that is v is equal to 3ti plus xzj plus t square yk. In this velocity vector, we get the u component of the velocity which is equal to 3t, and similarly v and w are given by xz and ty square respectively. Now calculating partial v over partial t, partial v over partial x, partial v over partial y and partial v over partial z as given in equation 2.7. Now using equation 2.7 in equation 2.6, we get the result in the form of equation star. This equation star denotes the total acceleration of the fluid particle. Now we present some basic definitions that will be used in derivation of the basic equation of the fluid mechanics, in which number first we present the volumetric flow rate. What is volumetric flow rate? The volume of a fluid passing through any normal cross section in unit time is called the volumetric flow rate or discharge. It is denoted by capital Q and its unit is meter cube per second. Similarly, what is mass flow rate? The mass flow rate, that is the mass of a fluid passing through any normal cross section, and unit time is called the mass flow rate. It is denoted by m star and its unit is kilogram per second. Now what is average velocity? Sometimes it is also called mean velocity. Average velocity is the ratio of the volumetric flow rate to the cross-section area of the surface. It is denoted by capital V to the subscript average and is given by Q divided by A. Volume flux to a surface. Before deriving the basic momentum and continuity equations, here we will establish a mathematical relation for the volume flux through a surface. This is the main part in the derivation of these basic equations. For this, consider the motion of an incompressible fluid through a surface S. Let V be the velocity of the fluid at some point phi of the surface. Divide this surface into m surface elements, that is del Sk, where k started from 1 up to m. Let Pk be any arbitrary point on the each surface element, that is del Sk. Now, Nk be any unit normal on the surface del Sk at the point Pk that moves with the velocity Vk, and let theta k be the angle between the unit normal and the velocity vector v. Now to find the normal component at the point pk, we use the basic dot product of the unit normal vector and the velocity vector vk, that is further is equal to vk cos theta k. That is the angle between the Vk and Nk is theta k. Now, the amount of fluid that flows in the unit normal n direction at the time delta t is given by equation 2.8. Now, the volume flux through the surface del Sk in this unit normal nk direction is given by equation 2.9. Now the volume flux through m different elements is given by equation 2.10. Here the summation k started from 1 up to m shows m different elements. So this is the summation of m different elements, because if we use k is equal to 1 we get the first element, and if we use k is equal to 2 we get the second elements, and so on. So these are m different elements on the surface S. So the volume of fluid through the whole surface is given by equation 2.11. Now if we take the limit of equation 2.10 as m tends to infinity, so we get the surface integral of v dot n ds. So the total flux through the surface S is given by this relation, that is the double integral of v dot n ds. Similarly, the mass flux through the surface S is given by equation 2.12. This is the same relation as given in equation 2.11, but here we replaced the velocity vector with the rho v. So that's why this is called the mass flux through the surface S. Now to understand the volumetric flow rate and average velocity, we present problem number 2. For the velocity vector v, that is given by this equation, evaluate the volumetric flow rate, that is q, and the average velocity through the square root vertices are given here. In solution, the surface with the given vertices can be plotted as, so this is the surface of the given vertices. Now the normal to the surface is, we are in the y direction, because this is the z axis, This is the x-axis and this is the y-axis. So normal to this surface is y-axis, so that's why here we present n hat is equal to the unit vector j. Here we have the velocity vector v that is given by this equation, and normal to the surface is equal to the unit normal along the y direction. So in dot product, the velocity vector v and the unit normal n is equal to xz. The remaining terms, that is in dot product, are equal to 0. So we get j dot j is equal to 1 and we get just xz. Thus the volumetric flow rate q is given by q is equal to the surface integral v dot nds. So we can write the surface ds as, that is dx dz divided by the magnitude of n dot j. Now, since the plane is placed in the xz plane, so we will get the limits on both the integral from 0 up to 2. Now in the denominator, the dot product and its magnitude of the unit normal and the unit vector along the y-axis is equal to 1. So we get the result xz dx and dz. First we integrate with respect to x, and using the fundamental theorem of calculus we get 0 to 2 2z and dz, and then integrating this term and using the fundamental theorem of calculus again we get q is equal to 4 meter cube per second. Now to find the area of the surface, since we have a square and the square of each side is equal to 2, so we get the total area is equal to 2 multiplied by 2, which is equal to 4 meters square. Now to calculate the average velocity or the mean velocity, that is further is equal to q divided by a, and the value of q is equal to 4 meter cube per second and the value of a is equal to 4 meter square, and so we get the average velocity is equal to 1 meter per second. Practice problems. In this lecture we discussed the material derivative and its derivation on the basis of an infinitesimal fluid element that flowing in the Cartesian plane. Problem number 1 states that derive the equation of material derivative for any physical or dynamical quantity h by using the concept of the total differential from calculus. Student will obtain the same closed form for the material derivative as we derived in this lecture by using the total differential concept from calculus. Problem number 2 is a simple problem. Here we are given three components of the velocity in which v and w are equal to 0. In part 1, find the local and convective accelerations. Part B, the general expression for acceleration when x, u0 and l are given. Find the local and convective acceleration. So you will use the definition of material derivative in which there are two parts. The first part is the local part and the second part is the convective part. So calculate both these parts, and then in the part B the general expression can be obtained by using the local and convective part by using these specific values. Finally, in references, all the materials in this lecture are provided from the given references. In conclusion, in this lecture we derived the basic material derivative by using the concept of infinitesimal fluid element, and then we solved a simple problem by calculating an acceleration for the velocity field. It is to be noted here that material derivative is not only used for calculating the acceleration, it is also used for finding the change in pressure, temperature, density, and other physical and dynamical quantities. And then we discussed in the later part of the lecture by volumetric flow rate, average velocity, and also discussed the mathematical form for the volumetric flow rate.